Have you ever thought about how the northern lights appear in the sky? They appear when charged particles from the sun collide with gases in Earth's atmosphere. Geomagnetic storms and intensified solar wind interaction with Earth's magnetosphere creates a stunning display of colorful lights. To truly understand this fascinating phenomenon, we first need to explore solar activity. Solar activity refers to the various dynamic phenomena happening on the sun, driven mainly by its complex magnetic field. This activity significantly impacts space weather and can influence the Earth's geomagnetic storms and the auroras. Here are the key components of solar activity. Sunspots. They are temporary, cooler areas on the sun's surface that appear darker than the surrounding regions. They form because of concentrated magnetic field flux, which inhibits convection and reduces surface temperature. Sunspots follow an approximately 11-year cycle, known as the solar cycle, with periods of maximum and minimum activity. Next up, solar flares. Solar flares are sudden intense bursts of radiation from the sun's atmosphere. They occur when magnetic energy that has built up in the solar atmosphere is suddenly released. These flares can release a significant amount of X-rays and ultraviolet radiation, disrupting satellite communications, GPS systems, and power grids on Earth. Now on to coronal mass ejections, or CMEs. CMEs are large explosions of plasma and magnetic field from the sun's corona. They can release billions of tons of solar materials into space, traveling millions of miles per hour. When directed towards Earth, CMEs can cause geomagnetic storms, leading to enhanced auroral activity and potential disruptions to electrical systems and communication networks. Let's not forget about the solar wind. The solar wind is a continuous flow of charged particles released from the upper atmosphere of the sun. It mainly consists of electrons, protons, and alpha particles. The solar wind interacts with the Earth's magnetic field, causing phenomena such as the magnetosphere and auroras. Variations in the solar wind can lead to geomagnetic storms. Events like these are not only visually stunning, but they also underscore the dynamic relationship between solar activity and the Earth's magnetic environment. We understood that auroras are created by interactions between solar wind, sunspots, solar flares, and CMEs. Let's now find out why auroras appear in different colors and patterns. The most common auroral color, green, is produced by oxygen molecules located about 60 miles above the Earth. Red auroras, which are rare, are produced by high-altitude oxygen at heights of up to 200 miles. When nitrogen is ionized, which means when nitrogen's electrons are stripped from its atoms, it can produce blue and purple auroras. Sometimes the colors mix, creating many different colors in the sky. Auroras often appear as curtains of light because the magnetic field lines create a structure that charged particles follow. These curtains can form arcs that stretch across the sky. The interaction of magnetic fields can also create swelling patterns or coronas when viewed from directly below. Generally, there are two locations for auroras. The first one, Aurora Borealis, which is the northern hemisphere. Common locations include Alaska, Canada, Norway, Sweden, Finland, and Russia. It is generally visible within the auroral zone, which is a ring-shaped region centered around the magnetic poles. The second one is Aurora Australis, or Southern Hemisphere, which is seen in Antarctica and parts of Australia, New Zealand, and the Southern Ocean. Scientists observe and study these phenomena through ground-based observatories like all-sky cameras, which capture wide-angle images of the sky to monitor aurora activity, and spectrometers, which analyze the light emitted by auroras to determine their composition. They use satellites like the NASA Themis mission that studies auroral substorms and their effects on Earth's magnetosphere. They also use imaging and magnetometer instruments to measure magnetic field disturbances and capture high-resolution images of auroral displays from space. We have space-based satellites like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory continuously monitor the sun for solar flares and CMEs.